So shall we start? So good morning, everyone. So it's it's like I always say that it's a pleasure to introduce a speaker, but this time it's especially a pleasure to introduce Simon Moon, because we know each other since many years ago from other times. So it's really a pleasure to have you here, Simon, in San Sebastian. So Simon Moon, he made his PhD in California, in UC Davis, under the supervision of Chuck Fadley. It was also, let's say, someone that was also important in my scientific lab. After a while, I think you spent some time in Intel, right? A brief period of time, but then he became beam scientist at the ALS in Berkeley. And then after many years of this, he went to Korea, where now he's a professor at Díez, Gwangju Institute of Science and Technology. I learned how to pronounce the name. And so thank you very much for visiting us, Simon. I hope that this is the first of many future visits to San Sebastian. And so, your turn.
Thank you. Thank you.
I'm sorry, just one thing. There are some people in Zoom. So after the seminar, there might be some questions online. So I will pass them to you.
Sure. Okay. Thank you. Thank you so much. Okay. Thank you. Before I begin, I really appreciate this arrangement and all this invitation. I really appreciate this. It's great to be here. It's such an honor to give a talk here. And I hope that I could give you some of the studies that I've been doing over the last few years, so that I could share the knowledge with you and maybe get advice as well. And so the title that I prepared today was a little bit more very specific about platinum-3 nickel and platinum-3 cobalt alloys using ambient pressure STM and XPS. Even though the title STM is there, but I'm not the expert on STM, so don't ask me any questions about STM. But I may be able to give you more answers to the XPS. So I'm from Díez. And you may, I don't know how many of you have been to Korea. I'm trying to convince Ricardo coming over to Korea many times, but just in case if you're coming ever visit Korea, this is the Seoul, and this is the North Korea, and this is the South. So this is Seoul capital, and it's about 2 hours away with the train toward the southwest. And this is the institute where I am. And it's actually relatively young. It's only about 30 years, established in 1993, and relatively large campus compared to the number of the students. It's very small. It's only about 3,000, less than 3,000. So we have a big real estate, but not enough students. But just we would like to keep it kind of concentrated and focused in science and technologies. And on the good day, you can see a very nice, cherry blossom on the spring days, and it's kind of a happy, jolly, small campus. And if you ever, visit Korea, happen to be in Korea, let me know. I'll be more than happy to show you around. Okay, so enough said that. I was going back to the title of the platinum and platinum alloys. Why am I studying this? Why was this so motivated us? Because this platinum alloys are actually very important catalyst for this hydrogen-based car. So, for example, this Hyundai, they introduced this hydrogen-based vehicle, and also the Toyota also using this fuel cell vehicle, and they all use platinum catalyst. And actually, they're using platinum cobalt specifically. And I met many people in this business, asked them specific questions about why are you using this cobalt, platinum cobalt, instead of other alloys? And they say this platinum cobalt works well, but in what they mean by works well means not only it functioning well, but it's also very stable over the times, and they said it has a better stabilities. So that's the big motivations in this community. And let me give you a little bit more about specific, how that actually works in platinum catalyst. And this is like platinum fuel cell one-on-one. Like one-on-one is actually it's very much like English and lecture title. So in hydrogen fuel cell, the hydrogen comes in toward the anode and get dissociated, and the detached electron actually traveling external circuit. But the other proton actually travels through the this membrane and in electrolyte basically. And then on the other, in the cathode layer, there's oxygen coming over and they get dissociated and then meeting with this protons and produce the water. And this process is dissociation of hydrogen. It's relatively easy. I mean, it's just a single step. But in here, this one oxygen has to be detached, and also that has to meet with this protons, and then have to make this reaction. So this process is awfully slow. From what I was told, it about 10,000 times slower than this. So this is actually the bottleneck where all the fuel cell and the technology is come into play. So this cathode requires catalyst to help this reaction, and platinum is the best so far. And platinum alloy and platinum, clearly, platinum is really expensive. And so the effort is, okay, platinum works well, but still very slow. And so the idea is if you could reduce, if you could improve, you need to improve the reaction process. And on top of that, it's very expensive. So you want to actually reduce the amount of the platinum. So the idea is actually replacing some of the platinum with a cheaper transition metal, for example, cobalt or nickel, then maybe you could help a little bit better. So, this was the very big kind of driving R&D effort during the Obama administration. During the Obama administration, the fuel cell, they were really pushing it. So around 2007, there were a series of the paper that came out from Berkeley and Oregon National Lab. And the idea was, if they could somehow replace some of the platinum with the nickel, then this, the normal reactions of the platinum by replacing this nickel with the underneath, they change this characteristics of the platinum, like tuning the electron structures, and then they can functioning somehow much easier. And this is the whole idea at the time. So they show this series of they test basically a series of the 3D transition metal with the all the series families: titanium, vanadium, iron, cobalt, nickel, and this pure platinum. They actually characterize this with the electrochemical the measurement. I don't know anything about this. Here, they characterize this material according to this so-called D-band center, which is the electronic structures. They compared that with the series of the reactions of the electrochemistry. They saw this platinum cobalt shows the actually highest reactions, and also platinum nickel is actually very near. So these two are showing the very good characteristics and performance, and they interpret it as like electrolyte is like something, something like electrolyte is you melt every transition metal. So they actually modeled it like this with the skin layers on the platinum on top, and underneath there is a transition metal that's sitting right next to it, and then tuning these electron structures. And they this is kind of compared. This is the theory part, and this is the experiment part. And then they're actually combining these two. So this was their idea. So 2007, this series of this paper came out, and everyone thought that, okay, maybe if you could just fabricate this platinum nanoparticle based on platinum and cobalt, then producing similar structures, then they could actually save 25% of platinum, which is a lot, and they could go out and build more cars and make it more industrial and friendly. The problem is, when you make this platinum alloys like this, I mean, many people tried it, but they ran into this called stability issue. In other words, this transition metal that was sitting below was actually start to leaching out because it started with the reaction. This oxygen start to push this transition metal to the surface, and that ruins the whole performance. So in the beginning, first few cycles it works really well, but after a few cycles it starts to deteriorate, and then the surface is actually now no longer valid. So this one was coming out in around that was 2007 and 2012. Many people actually run this follow up the idea, run this measurement, and they run into the similar issue. In the meantime, the group in the same guy actually, Boya, who I work with together, Boya came with some idea of this so-called nanoframe catalyst. He developed more nanoparticle engineering approach, and then they were able to make this very special type of nano frame which has a platinum skins on the surface. And then he tried to show this very stable with the many 10,000 time cycle. Still, this one runs actually very stable and it's very happy. So they were pushing it, but still, the platinum-3 nickel is not really the winners of the catalyst at the moment. The platinum cobalt is still doing this, replacing this platinum nickel. Nonetheless, even platinum cobalt also suffers a little bit of this stability issue. So this is the clear motivation that I wanted to introduce. There's another the idea of during this catalyst study, people also study this transition metal. I mean, this one is actually gold with the oxide underneath, and there is a fundamental studies about this strong metal support interaction. That has been also the approach to understand what's going on here too. So the bottom line is, I'm going to show you this one later, but the group from KAIST actually measured this approach, platinum-3 nickel. They bought this in a single crystal, and then they put the oxygen in, and they actually see how this platinum surface actually behaving. Because what they did was they prepared the platinum, they put the oxygen in this case the CO, but also here's the oxygen in. When you introduce the oxygen, the surface, this is the clean surface, and this is the oxygen surface, about 135 milliliter, which is not a lot, which is not even ambient pressure. You start to see this the roughening, and this is actually with the STM, you don't know which one is, whether this one is nickel or whether this is platinum. And they saw this one, and then they were questioning it. What are these, this nanoparticle? I mean, this particle that's coming up to the surface. So this was their first measurement with STM, and then we happened to run each other at the conference, and we discussed, okay, maybe we could do this together. So before I'm meeting them, actually I also was able to run this experiment. So platinum-3 nickel, if you anneal it, if you sputter anneal very clean surface, you will be able to have this very nice platinum 4F metallic state. And this is the platinum 111 single crystal. So if you compare this, having nickel alloy, this is the surface state that many people may know. This surface state is actually a little bit reduced, but you can see this clean, nice metallic state when you prepare the single crystal. Once you start to introduce small amount of the oxygen, 10⁻⁶, 100 milliliter, you start to see this, the shoulders coming up. If you measure the nickel around the same time, the nickel metallic state is now start to moving to the towards the left. And then you can start to see this forming of nickel oxide on the surface. And this right-hand side is the picture that reflects this situation. When you prepare very clean platinum alloys, you will see this platinum skin on the surface, which shows very clean metallic state. But once you start to put the oxygen in, you start to have this oxide of the nickel being pulled to the surface, forming this oxide. And this is exactly what we are seeing here. So I presented these pictures to them. And then they wanted to compare with this situation. So when we compared these two, we were able to find the condition that at a clean platinum skin surface, you see this fine metallic state. But when you introduce the oxygen about not a lot, at room temperature, not even high temperature, room temperature, about 100 millitol, you start to see this roughening. And we know that now that this clustering is actually not the platinum, it's actually the nickel that come up and they get oxidized. So here is the, by the way, so we see this nickel, and then we thought that, okay, then what are the chemical state of this? Well, this is nickel oxide that we just see it here. But then we thought that, okay, this one coming up to the surface, and how this one would react if we introduce other, such as CO. And when we introduce the CO here, which is the CO, it automatically actually produces the CO2 if it's very reactive enough. So that's the STM image they actually tried, and we run the same experiment at the beamline, and then we saw this initially oxygen sitting on the surface, and then when you introduce the CO, this one CO immediately replaced this oxygen, and then it just taken up all these oxygen atoms on the surface. So it is, in other words, it's very reactive. It's extremely reactive, and we saw this with the gas mass spec. We realized that when we introduce CO here, immediately when you introduce CO, the CO2 actually coming up very rapidly. So at that time, we saw, okay, well, we know what these are and how these atoms are reactive to the incoming CO, and we were happy. And then this is another, similar experiment, but basically we were able to correlate the idea of this, the metal oxide that forms on top of the nickel. We were able to correlate to this, reactivity and CO oxidation, how that occurs. And what we realized that was at the very surface here, at the very surface of this all small clustering is actually very reactive. Well, that's the idea of what we found from the experimentally. And so we went to the theorist and to explain this. And the DFT people suggest, okay, we have to try many model, but we sit down and thought about it. And then what we realized was this the oxygen that actually forming in here should interact with both platinum and nickel. In other words, platinum nickel interfacial oxide, probably the origins of this small clustering. And that when we calculated with the just forming nickel oxide and forming the platinum nickel interfacial oxide, when you compare these two, the energy of this reaction energy is much lower in these cases. So platinum nickel oxide interfacial oxide is probably what we are seeing. And at the time, okay, that's one approach. That's how we could interpret our experiment. So we moved on. So here the idea that because I'm going to actually refer this graph later on, is this oxide that being formed is actually coming through to the top surface with the breaking this kind of terrace. It's not coming from the step. It's from the terrace. Somehow it's coming up, and that means it's actually 111 surface under the oxygen is actually not stable. It'll actually lost. I'm sorry. This previously platinum 110. This is the platinum 110 STM image that we saw at the time, this was our measurement. At the time, we saw similar, this nano clustering on the STM on the surface. And when we introduce oxygen, we start to see this platinum is actually showing this oxide features of all this. But in platinum-3 nickel, we didn't see any of those. In other words, even though there's similar structures like this and similar structures like that, actually the chemical state is different. And that really, that was really our kind of thing that we couldn't quite understand, because we thought we should see something like this, but nickel is actually not. So at the time, that was our homework. And then, so we got encouraged by this. So we continued our study on platinum-3 cobalt, because that's actually the material that actively used in the industry. So we at the time now, we kind of work together. We know each other. So now during this measurement, they actually communicating together, and we run this experiment of basically same experiment of platinum-3 nickel, but platinum-3 cobalt is now is the substrate. So I will explain this one later. So first, under UHB, you prepare very nice STM images, very nice, clean, sharp, and when you introduce about 100 milliliter, basically, when you introduce that oxygen, you start to see very small changes, but not a lot. But when you introduce about 500.5 torr, 500 millitorr, and if you increase the temperature, you start to see this, it's not even a clustering. Actually, this is almost like a solid oxide that's being formed on the terrace. And also this step is actually completely ruined. And furthermore, we run the CO oxidation experiment further. But just looking at here, this oxide, the size of the oxide is completely different from platinum-3 nickel that we just saw. So obviously, platinum-3 cobalt is actually runs differently. So, so this was the STM image, and then we were actually following all this step together with the oh, okay. I have a movie that I would like to show you this movie. Thank you so much. Okay, so I'll launch the movie. So we cleaned crystal. I'm showing you the oxygen 1s, and then when we introduce the oxygen, you start to see this, the gas phase of oxygen with the small oxide. And when you introduce the oxygen up to about 500 millitorr with the increasing the temperature, you can clearly see these formations of oxide. And then you reduce the oxygen, and then I introduced a small amount of the CO. And then as soon as you introduce the CO, you start to see the changes of this oxide completely. And then when you increase the further temperature, this one starts to actually change it a little further. But then when you temperature down, and then it goes back, and this oxide remains on the surface. In other words, what we are seeing here at temperature of about 450 and pressures of 500 millitorr is something we are seeing somewhere here. And this is a big, blob of this oxygen 1s. It's actually reflecting the chemical state of all this. And there is no single state. Actually, there are many, state of the oxygen that actually, some of them are getting actually reduced, and some of them are remaining strong. And this is due to the reaction with the CO. But the thing is, when we introduce, when we actually look at the platinum, we did actually exactly the same step. So we introduced the platinum 500 millitorrs of the oxygen. We look at the platinum 4F, and what we saw at 500 milliliter about this pressure, we start to see this shoulder on the platinum 4F, which we didn't see it in platinum nickel. And platinum cobalt is clearly different. And when we introduce, it's exactly the similar as in the previous case, when we introduced a small CO and then increasing the temperature, this oxide is actually now being completely reduced. And then this is oxygen, this oxide that actually attached to this platinum somehow here is actually representing this state of this oxygen is being actually reactive. And I'm sorry, I need to go to the next one. And then what about cobalt? Yes, cobalt will get oxidized. And under clean surface, you see this metallic state. And when we introduce this oxygen, 500 milliliters, same pressure, and you can start to see this is a little, broadening. And then this actually if you follow this edges of the metallic state, you can see slightly shifting towards backward. And clearly, when you introduce 550K, and you introduce 500 milliliters of oxygen at this temperature, this one representing this, the cobalt coming up to the surface and gets oxidized. And then again, when you introduce the CO, you start to see these reactions of some of it. But as you can see, this is not fully actually, going back to the metallic state. It still, has a broad, features, which means maintaining this oxygen, cobalt oxide state. So, if you stop here, when we compare this platinum-3 cobalt and platinum-3 nickel, both 2p state, which is metallic state, the transition metal oxidation state, both of them shows strong oxidations when you introduce the oxygen. Nickel, similar, cobalt, you can see this oxidation more prominently because this one is shifted quite a lot, and also this one quite shifted a lot. So in transition metal, it's clear that it gets oxidized, no doubt. But then this somehow is not following as I actually like. But when you look at the platinum 4F, platinum chemical state, nickel, as I said before, when you form the oxide on the surface of the with the nickel oxide, the platinum still remains as a metallic state. But platinum cobalt, no, it's not. It's actually showing this clear the oxidation state on the synapse. And this one clearly indicates that cobalt is different from nickel. And this platinum alloy is actually, platinum nickel alloy is actually somehow maintaining their own characteristics of metal, but cobalt is not. And so we were wondering where that is coming from. So what we did was at this 500 milliliters of oxygen with temperatures about 550 K, and that's the cobalt oxide. And we did the energy scan, so we know where this oxygen is coming from. And this 350 is more surface sensitive, 650 is more bulk sensitive, and you can see that more features can be seen at surface sensitive features. So this one is on the surface. That's that one for sure. So we identify at least that oxide exists on the surface. And then when we put the CO, this is kind of, we witnessed this from here too, but we wanted to confirm that when we introduce the CO interacting with this oxygen 500 milliliter, we start to see clearly that this oxide that was attached to the platinum is all gone. But in the metallic state, it was always clean. So throughout the surface sensitive to the bulk sensitive, everything now becomes actually clean. That means its oxide is actually reacted to the CO. That's actually something that we see. And this is then what we did was we tried whether that oxide that disappeared could regrow if we introduce the oxygen 500 milliliters with 550 cal. When you introduce the temperature, would we be able to grow the oxide again? And unfortunately not. The oxide doesn't grow that much. So it kind of it happened during the oxygen being segregated to the surface. It forms the oxide. It reacts to the CO. But once you're done, it's very difficult to regrow the oxide. There's a small amount of the oxygen, but it's not a lot. It's not as much as before. So that's what we saw. And what about cobalt? Previously, I said in the case of platinum-3 nickel, I have a platinum nickel interfacial oxide. But what about cobalt? Can we identify a little more further so that you could model the system? But it turns out to be it's not easy because in the case of platinum cobalt, this chemical state that you can see from the 2P level, it's not really, it's not really distinct. And we look for the references, and this is by far probably the best reference that we could compare. They actually grow the cobalt oxide on the surface of, I think it was the substrate was platinum, I think. So that somehow they grow this deposit cobalt and they grow the oxide. They check the lead, and they actually they were able to confirm this chemical state, and they check this they measured this cobalt 2P, and they were able to fit this data. Well, it's very difficult to do the peak fitting of the transition metal 2P state, especially. There are many actually process that involved, but nonetheless, this one were able to give some guideline of this chemical state of the cobalt, and this is oxide. So, and this is CO3O4 and then COO. And then based on this, we could kind of estimate that we might have something in between, some mixed state, which is fine. So we actually try to fit it, and this fitting, it can be very, very challenging to our, later on we'll run another experiment. We try to increase the temperature, increase the photon energy, so reduce the background, and we were trying to fit it, and it worked out relatively okay, but we're still scratching our head whether that is really the case. So comes down to the these two comparison of platinum-3 nickel and platinum-3 cobalt. Clearly at around 100 milliliters of similar pressure, 100 milliliters of oxygen in room temperature, and this is 100 milliliters of the room temperature, is clearly different. And platinum cobalt, it seems more stable at this temperature. At this temperature, at this pressure, it's okay. But when you increase the temperature a little further, then it's completely different. Here, this is like almost one-to-one comparison. So when we introduce clean surface, this is the clean skin surface. It's almost identical. And when we introduce, this is the CO, so don't look at this one. So when you introduce the oxygen, about 100 millitol, this is the surface of the platinum cobalt. This is the platinum of the nickel. And the scale is, I know this is 30 nanometer, this is 10 nanometers. The scale is a little different, but you don't see this much in here. And by the time when you increase the temperature a little further, you saw this more, big island of this. But of course, we introduced a little bit of more temperature than room temperature. But oxide that being formed on the surface is more bigger, more stronger, and so these are the differences. And we think that because of this, platinum cobalt, you form this, you can see this oxidations of the platinum. Platinum nickel, you don't see it. And this is the big difference of these two systems, which we think that platinum-3 cobalt, when the cobalt come up to the surface and forms the oxide is actually very stable. And that actually creates a lot of defect. This is still we are actually guessing. And that defect actually creating enough space that disturbs this platinum, and the platinum gets oxidized. Nickel, no, nickel just small platinum just coming up to the surface, but that oxide is not stable enough. That's actually very small, remains small, not actually getting enlarged. And this one is it's another reason that you don't see the oxidations of the platinum. That's not enough to get disturbed the platinum, but in the cobalt, it does. When I talk about this, just not scientifically, just roughly with the electrochemist, they said platinum-3 cobalt is more stable in some respect. Once you form an oxide, this one will become more stable, more solid oxide than the nickel oxide. So we are actually at the moment talking to the theoretician and then trying to figure out what the chemical state is that this one is coming from. So with that, actually, I would like to just kind of summarize what I have. So platinum-3 nickel, platinum-3 cobalt, we clearly see this different chemical state of the platinum. And under the C oxidation, like reaction studies, nickel shows very dynamic state that changes dramatically, but the cobalt still remains on the surface, and the reaction is not as distinct as a platinum-3 nickel. And another possible scheme is in platinum nickel, you have this sharing this platinum and the nickel coming up to the surface, and then sharing this oxygen and forming this platinum nickel interfacial oxide. But in the case of the platinum cobalt, it forms a very stable oxide on the surface that doesn't really shares too much. And the platinum that shares the oxygen, this one gets actually activated and then get reduced. The first half of platinum-3 nickel, we kind of more or less wrap up the study, but platinum-3 cobalt, we are still working with this DFT calculation and trying to explain what we just saw. And this was actually a lot of effort with the many different facility, and mostly this KAIST Jeongyeong Park and Jongjin Kim, they did this STM measurement. And then in the meantime, I was communicating with many people at different synchronization facility. One is the Soleil and the Photon Factory, which I couldn't include here, but I also majored at the Brookhaven National Lab, and we repeat the measurement. We had a much better high resolution data that I didn't prepare today, but that also exactly in line with what I just discussed. So we are working on this one, and I would like to thank all our students who actually spend day and night with us. This experiment was actually almost took us about 3 years. This is Jeongyeong Park, and this is Professor Kondo, who gave us some of the beam time at photon factories and this Pohang light source. And so lastly, I would like to actually mention about this. When first ambient pressure XPS came up, there were 2 different schools, and one of them was the Gunther Rohrfechter. He wrote these articles on I think it was the Journal of Physics Condensed Matter, and the title was, this ambient pressure experiment is pretty important, mind the gap. And on the other hand, Professor Goodman, who passed away, unfortunately, he was around the similar time, around 2008. He gave us this talk at the UC Santa Barbara, I think, remember? Yeah. And then the title was this, UHB to elevated pressure, never mind the gap. He has a very different, thing. Well, of course, I perfectly understand his argument. His argument was the thing that has been carried out over many years in surface science is still all valid, and it is all still many basic mechanism can be understood. I perfectly understand, but then when I see this experiment as I'm running with the ambient pressure XPS, we start to see something a little different. And there are many other reasons, but that start to seeing at about 100 millitours, little bit of the pressure that coming from molecular flow to the viscous flow. That region is about 100 millitol, about millitol region. Then you start to see this a lot of these unexpected things, and that might be explaining some of this in a pressure gap science. But again, there are a lot of other approaches. In this case, especially, I personally think that defect is another issue also. Defect can be more severely, start to interact with the gases. And recently, I started to work with the CO2 absorption, and that CO2 doesn't react. But when you introduce high pressure, it starts to react. And that also probably referring some of this in the pressure gap business maybe. So with that, I'll stop here, and then I'll take any questions, and thank you for your attention.
So thank you very much, Simon. Just one comment. If there's anyone online that would like to make a question, please send it to the chat, okay?
Yeah, your last comment about molecular flow versus viscous flow, what means? What was it?
So molecular flow is under UHB. It's actually the collision is rare, like up to 10 to the minus 4, 5 maybe, up to that region. The pump, because I'm using this the terminology when I was learning about this vacuum technology. So under UHB, everything is actually molecular flow, just like one atom just hitting. But when you start to increase the pressure, then you start to kind of start to flow at some at certain that is difficult to distinct exactly where it is. But when you, for example, when you're using the turbo pump to, I have to go back from mechanical pump to the turbo pump. In between, there is you have to turn on the switch back on, right? So once you have reached enough pressure, then you can turn on the turbo. So this huge amount of gas flow is being taken care of by this mechanical pump. And that flow is mostly involved with this viscous flow. But then once you start to turn the turbo pump and it works really start to now pump much lower pressure, but that is actually start to going into the regions of molecular flow. So that in between is the region that we start to see these things. Like 100 millitol, 1 millitol, even 1 millitol, we start to see this, some of the trend. I can show you some of the data of CO2 experiment that we did. So what we did was we prepared CO2 on platinum 111, copper 111, exactly the same thing. 1,000 Langmuir, no changes. 10 to the minus 6, no changes. 10 to the minus 5, no changes. When you introduce 1 millitol, you start to see the changes. And we don't know why. And only thing that explains at the moment about CO2 dissociation on this surface is actually the molecule being squashed on the surface, and then kind of creating the band structures, and then start to get charge transfer more from the surface and then get dissociated. And that's the idea of that, the CO2 dissociation business. That was actually suggested by High Freund. And similar things, we start to seeing it here too. I just saw this oxygen on platinum 3 nickel. Underneath 10 to the minus 6 millitol, I don't see change. I show it to you. We don't see changes. But about 100 millitol at room temperature, I start to see this, this start to being pulled to the surface. And so the way that I try to figure out at the moment is, single crystal, no matter how you prepare, it's clean. It's good. Everything looks fine. But there's always defect. There's always steps. And this step, defect may not play really, any role under UHB condition. But once you start to put a lot of molecules just forcing into the surface, that start to come into play and they start to react. That's But that's very difficult because the fact is you cannot model it. I talked to, when I was grad student, when I don't know anything about DFT, and I talked to them, can you calculate defect? And no, that's not easy. And so with the help of the STM, we start to see some of the evidence, maybe partial evidence, not direct evidence, but we start to see some changes due to this, elevated pressure, and that start to happening at mostly at this steps, not terrace too much. I mean, always, terrace, the step is the first that start to get oxidized or forming the cluster, and then the atoms start to moving away, or sometimes the terrace actually taking over too. But we already see this in a step is the where the action takes place, and that terrace, I mean that step has the place where that oxygen can easily go into it and pull this transition matter underneath. So I'm guessing it because I cannot see. But from this business, I mean, the Professor Goodman, I respect his work. I fully agree with his argument about this situation, because his argument is about, if you just trying to understand atom surface science approach one-on-one, it's perfectly fine, it works. But in real life, it seems the crystal is not really 100% perfect crystal. It seems there is always the gap. I mean, that gap is probably the defect or partially impurity. And recently I burned by this, tin contamination on gallium element. So that's how I see it. That's how I actually kind of guessing it in a sense. And also it happened to be always happening during this 10 to 100 millitole region. And that around that time is always we start to see this. I can go on and on this one because I have another. I can talk about palladium for all days. Palladium completely different.
Right. Yeah, that's a question.
Just a follow-on question, then. I mean, then how useful is it at the moment to use single crystal in your study? I mean, if you believe at the end that you destroy a single crystal, that the steps are more important, that the tin comes out, or whatever, how useful is it to start with single crystals?
Very good. I like your. I mean, that's very good question. First, the single crystal, it serves the purpose as a model system, right? We know where we can start with, and then we can characterize 111, 100, open surface, nearest atoms, and I mean, all kinds of things can be actually studied systematically. But then when we start to look at this situation, I start to really wonder, if we can somehow control the defect, and then we can control the defect on the single crystal, then I should be able to do some, correlation study. But unfortunately, it's very difficult to control the defect. And I remember there was one article long time ago, the group in Japan, what they did was they controlled the numbers of the steps, and then they made systematic studies, and then they contribute that, okay, step is actually very important. And that might be related to what, this defect study can be actually correlated to. That's my just, at the moment, best answers that I can give. But this defect is actually really, it comes, especially this pressure business. It's very hard to ignore, and we have to pay attention to this. Yes.
So in the beginning, you said that the cell is most efficient when the position of the D band is around 3 point something. Is there what's the reason for that?
Oh yeah, so the D-band center is actually is suggested by the Danish. That's right. So in the DFT calculation, they actually look at the trend, and they look at all the reaction trend, and then they saw that, oh, this, previously people thought that the highest and the density of the Fermi level is probably the most reactive, because that one is readily available to the charge transfer. But it turns out that he realized the whole D-band, the weight of the center is actually more relevant. It worked really well. But then there was many other cases too. I mean, then later he said, oh, not only the D-band width, D-band center, but D-band width is also important. And also some group came up with many other ideas. So now he's saying that this is the explaining general trend, but not necessarily. In some cases, it can be different. And in this case, at that time, 2007, D-band center was hot. And we were actually collaborating with the Northcote too. Northcote was actually, there was another parallel paper came out in Angevante, and he used basically the same data, but he wrote it in terms of this D-band approach. And now people don't say too much about D-band center. I mean, even though it works well, I mean, it works general trend very well. I think he did a very good work. Excellent. So it gives you a very good idea. But now, for example, like a defect, no. There's or if you have a lot of step, no, it's not going to work. So D-band center is, I'll leave it at there. But I also myself try to calculate D-band center and correlate some of the trend. General trend is working well. General trend. But not
also, if I may, I assume that the actual electrodes are not single crystals, but some nanoparticles.
Oh yeah, then if it is nanoparticle, well, okay, so the reason this paper got accepted in Science and Nature Material, and the reason that this one was actually getting a lot of attention was instead of they were electrochemicists who actually making this nanoparticle and testing this performance, they were making a lot of trial and errors and doing the other composition. But then at the time, this Nana and Boya and Phil Ross group, they said, okay, instead of just trying many bake and shake approach, maybe we can just systematically testing this material with the approaches of electronic structure. So with the different electronic structures to this platinum-3 nickel, platinum-3 cobalt, they were able to mimic that. They were able to mimic that. This is actually what's happening in electrolyte. Electrolyte, once you put into a nanoparticle into the surface, nanoparticle into the electrolyte, every transition metal on the surface is being melted. It's all gone. And you're going to have this kind of skeleton surface on top. And this one is very difficult to model it. But if you're using the single crystal and annealing it, then the transition metal will melt underneath and then forming the platinum-3 nickel, forming the platinum skin surface. Then this one can be correlated to this. So they were able to prepare this many different single crystal in a systematic manner. And then they were able to suggest that, okay, if you do this platinum-3 cobalt, platinum-3 nickel, you'll get a very good performance. So that was actually their approach in a different direction. Instead of preparing the nanoparticle, they prepared the single crystal and then kind of giving them kind of big pictures. This is the approach that you want to have, and focusing on to somewhere here. So that's the reason they kind of got attentions, and many people actually followed. And it turns out that this is the case where the platinum-3 cobalt is very reactive and very effective. So that's their approach, and at that time was deeply appreciated by the community.
But the thing that you essentially, as I understood, you want to avoid is to transition metal to get to the surface.
Yeah, well, so that's the this is 2007, so now it's almost 15 years. It turns out that platinum-3 nickel is still leaching out. It's very difficult to maintain that stability over many cycles. Platinum cobalt, somehow it works better than platinum-3 nickel, and they said it has a better cycle lifetime. And the thing that I discussed here, everything about platinum cobalt forming up the oxide and everything, in actual electrolyte, it may not work. It may all just leach it out, and it may not be useful. It may not be really helpful. But somehow along this way, I mean, so I'm because I'm preparing the manuscript, we're trying to figure out how to present our approach. To me, this oxide that come up to the surface probably melted away with the reactions, and the surface become roughened like this. But this surface is somehow more stable than platinum-3 nickel, and that one we are trying to understand how really this this transition metal underneath is actually behaving. But that's really too difficult. I met one scientist who's working with Toyota directly. So I went there and I just asked very blunt questions. Why are you using platinum-3 cobalt? And she was saying that this is performing well, but I mean, I shouldn't say she, but the scientist said, no, it's not clear. Especially this, how the cobalt behaves inside of the electrolyte, no. Because there's not many tools. There are only few tools available to look at this behaviors of this in situ. X-ray scattering is one of them, but it's very difficult to interpret. You need this also the theory. Yeah.
Okay, so I think we can stop here. So Simon will be here also this afternoon in case any of you are interested in discussing with him. And so thank you very much again for your talk, Simon.
Sorry for the mix-up. Okay, so thank you. So how do I start this? 어떻게 하지? 아니 이게 지금 움직이질 않나? 됐어 이제 됐어.
Yeah.